this is 20 volt battery, this is 20 volt battery, if a polarity like this, positive, negative, there will not be any flow of current and galvanometer will not register any reading. If we say this is 20 volt battery, there is a galvanometer, there is a resistor, and this EMF we don't know, but the deflection is equal to 0. Now if we have arrangement like this, if the deflection is equal to 0, so we can very easily, we can very comfortably, confidently we can say that this E should be equal to 20 volt only. That's why there is no deflection. This is primarily the kind of arrangement we have in potentiometer. Now let's try to relate this principle with the working of a potentiometer, that is how this is used to find the EMF of an unknown battery. So over here what we have is, we have a resistance wire, we have a long resistance wire, say 100 centimeter, and this resistance per unit length is constant, that is it has a uniform resistance per unit length. And when we connect it to a battery, let's say 100 volt, this is positive terminal, this is negative terminal, so obviously the conventional current shall be flowing in this direction. When the conventional current is flowing in this direction, it means the potential of A is greater than potential of B, and the potential difference between A and B, it has to be 100 volt only. On the length of 100 centimeter, we have a potential drop of 100 volt, and this potential drop is uniform throughout the length. So it means if we divide 100 volt by 100 centimeter, so we get, that is potential gradient. It is 1 volt per centimeter, that is for every 1 centimeter, the potential is falling by 1 volt for every 1 centimeter. That is a potential gradient or potential drop for every 1 centimeter. And if we say there is a point, let's say C point is over here, and from here to here, this length is suppose 30 centimeter. We wish to find out what is the potential difference between A and C. Now if we say for every 1 centimeter, the potential drop is 1 volt. So obviously for 30 centimeter, A is going to be 30 volt. If we say 30 volt, so it means this is going to be at higher potential, this is going to be lower potential. So between A and C, this resistance wire is kind of working as a source of variable potential difference. If we have a D point over here at a distance of 20 centimeter, if we say at 20 centimeter over here, so if we say this is A, this is C, then the potential difference between A and C is something like 20 volt only. As we increase the length, then this polarity, then this potential difference is obviously going to increase only. Now what we do, in addition to this battery, which has a negligible resistance, we are trying to find the EMF of other battery which also has a negligible resistance. Now let's say we have a battery whose EMF we don't know. So what we do is, we connect this point to this, and over here we have a galvanometer and we have a jockey or slider. This slider can slide over this resistance wire. We can tap it over here also, we can tap it at distance of 30 centimeter also, we can tap it at 40 centimeter also, we can tap at the end also. So as we change the length, certainly the potential difference between this point and let's call this a C point, the potential difference will be increasing. If we try to relate this with this, so this 20 volt battery is something like this, and this EMF, we wish to find the EMF of this battery. Let's assume this length is 20 centimeter. Let's assume this is 20 centimeter and the galvanometer reading is 0. If this length is 20 centimeter, so that is equivalent to a potential difference of, because for every 1 centimeter we have 1 volt. Now we know that is for every 1 centimeter there is a drop of 1 volt. So it means if this is 20 centimeter, we are going to have a potential difference of 20 volt only. So potential difference, if this length is 20 centimeter and we know for this configuration it is 1 volt per centimeter, so for 20 centimeter length it is going to 20 volt only. So this is going to be 20 volt if this is 20 centimeter, and this being at a higher potential as compared to this. And for this configuration we see that is there is no galvanometer deflection. The needle of galvanometer doesn't deflect, it stays at 0. It means whatsoever is the potential difference between this, the same is going to potential difference between this, that this and this is kind of same. So the EMF of this is going to be 20 volt only. So when we are tapping it over here, primarily we are looking for a null point. Null point is that point when there is no deflection in the galvanometer. When there is no deflection, whatsoever the potential difference across these points A and C, the same will be the EMF of this battery, because at this moment the current will not be flowing in the circuit. So that's why it is going to the EMF of this battery, it is not going to the potential difference of this battery. And now if this is 20 volt and we tap this resistance at 10 centimeter only, so this will work as a 10 volt only. So the current will flow in this direction, galvanometer will show deflection in one way. And if we tap it at 40 centimeter, so this is going to be a 40 volt battery, kind of 40 volt battery, so the current will flow in this direction and the deflection will be in the other direction. If we tap it exactly at 20 centimeter, so this is also 20, this is also 20 volt, and there will not be any deflection in the galvanometer. This is primarily the principle to find the EMF of this battery. On the same lines we can say, if we know the EMF of this battery and there is a resistance wire, so the potential drop across AB of length L is E1 by L. So this is potential gradient. So this is potential gradient. And now we take this battery with a galvanometer. This is E2 and we have to find the value of E2. Now we tap it over here and we go for a null point. Let's say over here we get a null point. If this length is very small, then obviously the potential difference between these 2 points will be less. This will work like a stronger battery, the current will flow in this direction. If it taps C over here at a greater length, then obviously the potential difference between these 2 points will be more and the current will be flowing in this direction, the deflection will be in the other direction. But as soon as we get a null point, that this is a null point, so it means the potential difference between this and point C is same as the EMF of this battery, and that's why we have a null point. Let's say we get the null point at a length small l. So what is the potential difference between A and C now if C is now the null point at a distance L from point A? So it is going to be E1 by L, that is potential gradient, potential drop per unit length into L. So this is going to be the EMF of, so this is going to be the EMF of battery 2. So now we can easily say that if greater is the length, then certainly greater will be the EMF. That is, EMF of this battery is directly proportional to the length L. If we have to compare the two batteries, let's say now its EMF is E and we have this EMF battery, let's say E1, first we put the battery EMF, and let's say we have first battery whose EMF has to be compared with the other battery and its EMF is E1 and the corresponding length is L1. So it means E1 is proportional to L1. Now what we do is we replace it by a second battery and now the null point is at a distance L2. So obviously E2 EMF of this is proportional to L2, proportionality sign being constant for both of them. So we see E1 by E2 is equal to L1 by L2. So out of the two EMFs, even if we know one EMF, we can find the EMF of the other one, or we can directly compare, that is E1 by E2 is equal to L1 by L2. L1, L2 we have measured it because there is scale also in potentiometer. Now if we have to get a very accurate value of E2, we can do two things at least. One is we can increase the length of this wire, resistance wire, so that the potential gradient is small, that is the potential drop per unit length is small. Generally this resistance wire is of Eureka or manganese, and there are multiple such wires to increase the length so that we have a more accurate reading of E2. To have an accurate reading of E2, also we use a more sensitive galvanometer, so that even for a small change of current in this, there is a large deflection that can be noticed. So this is primarily how we use this principle to find the EMF of unknown battery. Using the same principle, we can also compare the EMF of two batteries because we have a corresponding length for their null points.